Hi everyone, I'm Michael. I am working on DSPy. I am a master's student at Stanford, and this summer I'm a research intern at Snowflake. So I got involved with DSPy working on the prompt optimization part of DSPy along with Krista Opsalong and Josh Pertel. So we make up the prompt optimization team within DSPy. And the title, so because I work on prompt optimization, the title of the talk here is DSPy Prompt Optimization for LM Programs. But I hope by the end of the talk, I convince you that the power of DSPy is actually in the abstraction behind it and how it makes you think about your problems. And then the optimization itself can be abstracted away to the framework. So right now we do prompt optimization and fine tuning, but if something comes along tomorrow, a brand new way to adapt language models, DSPy can adapt to that as well. And so you're not stuck in one optimization framework. So it's never been easier to build AI-powered applications. So for example, ChatGPT is the one everybody knows. And if I ask where is GitHub headquarters, it accurately tells me where we are right now. However, turning monolithic language models into reliable AI systems remains challenging. So if I ask ChatGPT when was Stanford University founded, it'll tell me actually the incorrect date. That's the date that it opened, not the date that it was founded. And if you ask who it was named after, it'll tell you Leland Stanford, when in fact it was named after Leland Stanford Jr. So LLMs are prone to hallucinations. We know that that's an issue. And this has real world consequences. So this is a story that is well known now that Air Canada had a chatbot that was doing customer service, and it told a customer that they could get a discount, and then Air Canada didn't want to honor that discount because the chatbot made it up, and it got taken to court, and they actually did have to honor the discount that the chatbot made up. So it's very important that chatbots are reliable and do what you want them to. So every AI system is going to make mistakes, at least the way that LLMs are set up currently. And the monolithic nature of language models makes them hard to control, debug, and improve. But we already know how to build controllable systems and also how to improve them modularly, and that is called programming. So that's already something that we do. So this is where DSPy enters. DSPy is the framework for programming, not prompting your language models. And what do I mean by that? I'm going to go into detail here. So with DSPy, you're actually using language models to build and optimize modular programs. Instead of optimizing the model, like I'm going to fine-tune the latest iteration of Llama, I'm going to build a compound system that calls Llama 3 times in these 3 ways, and I can optimize each of those calls. And these LM programs are more accurate, transparent, and efficient than language models in isolation. So instead of tweaking brittle prompts, here's a prompt that was human engineered for a retrieval augmented generation problem, a multi-hop retrieval problem. So you would ask a question that needs you to reason over multiple documents. And so a human prompt engineer wrote this really nice prompt for GPT 3.5. You can take a moment and look at it, but it's very complicated, and it covers a lot of details about how the language model should be thinking about this problem. And if you run this on Hotpot QA, you'll get 33% accuracy on GPT 3.5. So it's a good prompt, but it takes a lot of work to build something like this. Instead, you can write a short language model program in Python and automatically optimize your prompts. And essentially, the program will learn how to use the language model effectively. So one thing that this affords you is composition via control flow. So let's take a look. This is an actual DSPy program. So I'll go through this step by step and explain how this works. But essentially, you can see we have a forward pass. So this is inspired by PyTorch. And the input is a question. So in this multi-hop retrieval setting, we might have a question that requires you to reason over several documents, and that's the input to your program. And we're building up a context. So we actually have just normal Python syntax, and we have this for loop where we say we're going to loop over this 2 times. We'll generate a search query. We'll use some sort of back-end retrieval engine. So this could be a SQL database. This could be a Colbert index. Whatever retriever, whatever vector or graph retriever you have set up, and we'll retrieve documents based on that search query. We'll search again based on whatever documents you got. Maybe it didn't fully answer the question, maybe you need more details, so we'll write a second search query. We'll search again, and finally, using all the documents we retrieved, we produce a final answer. So this is our retrieval augmented generation program in DSPy. And these are our two language model calls here, the generate query and generate answer. So we have really abstracted all of the language model calls into these two lines. And you also have declarative layers. So what we can do is define what these language model calls should look like. And so in DSPy, we call this a module. It's all very inspired by PyTorch. So you can define self.generateQuery to be a chain of thought call that takes in a context, a question, and produces a query. And generate answer should be a chain of thought call that takes in a context and a question and produces an answer. So given this, what we've actually defined here is just what the inputs and outputs to our language model should be, but we haven't put any work into prompt engineering how the language model actually gets called. And now, given this, we can automatically optimize all of our calls to the language model. So really briefly, I want to show a diagram of how will you, like, imagine this program. Every time you see this, this kind of stylized llama thing, think about the DSPy program behind the scenes. But we'll be using this stylized one going forward. But we have our two llama calls and our one retrieval in the middle. So let me talk a bit about how we optimize the prompts in this program. So if you look here, this is one of our declarative calls to the language model where we say we want a chain of thought prompt that takes in a context question and produces a query. So how does this work? Well, signatures, which are what we call the context question to query part, are compiled into prompts using a template to start. And we'll optimize from there. But they start with a template. And so the signatures define our inputs and outputs. And then we put them through this template that is a predefined template just to compile into a basic prompt. And it'll end up looking something like this. So given the field's context in question, respond with the field query. And we just say, follow the following format and give it the specific things that we want. And of course, because this is a chain of thought, we'll also ask, think step by step. So that's how DSPy will automatically write your prompts for you, but that's not an optimized prompt, that's a default template prompt. So I'm going to talk more about how we can further optimize this prompt jointly along with all of the other prompts in your program. So here's our starter prompt. Given the field's context in question, respond with the field query. And this might have a score of, say, 37. So the way we compute this score is we have a bunch of input questions, and we know the correct answers to them. And we compute an exact match accuracy when you run your program on this validation set. And the inputs and metric can be varied to whatever task you're working on. This doesn't have to be a retrieval augmented generation setting. So using an optimizer like MIPRO V2, which is the optimizer that Krista and I created, you can compile your program and it will produce a prompt, something more like this. You will be provided with a question along with a set of documents that we've already found to help answer the question. And it gives some examples. So for the interest of space, I've cut this off, but it'll produce few-shot demonstrations and plug those into the prompt as well. And something like this might get a score of, say, 55% on your validation set. So let's look closer at an example prompt. So here we have this self.generateQuery prompt, and this will have, it will parameterize it into a few components. So first of all, we want a plain text instruction that describes what you're trying to do. And so in this case, we have carefully read the provided context in question. Your task is to formulate a concise and relevant query, and so on. And then we put in few-shot demonstrations that we will bootstrap ourselves. So I will talk about how we find these later, but you can see here is the context. Remember, the signature defined that we wanted a context and a question and write that into a query. So we say, here's our context about Twilight, the mystery series, and here's our question. In which year was the first vampire-themed fantasy romance novel for the Twilight cycle published? And then we have reasoning, so let's determine when this was first published, so on and so forth. And we have our output, which is the search query. When was the first vampire-themed fantasy romance novel published, which we would use to get more context. And so given this and input, this is a full demonstration of what your language model should do in this situation. It should take in the context question, it should produce reasoning because we said we wanted to do chain of thought, and it should produce a search query as its output. And we can just find another few-shot demonstration and put that in the prompt as well. So this is the sort of thing that DSPy will produce entirely for you, and all you have to provide is that top line. So it will find all of this in between. So doing this, we can actually get 55% accuracy on the same benchmark with GPT 3.5, as opposed to 33% with the human-engineered prompt. We can get 50% with a much smaller model, Llama 2, 13 billion, and with an even much more incredibly smaller model, T5, 770 million parameters, we can get 39% accuracy with an additional fine-tuning step, where essentially we do this bootstrapping process to find example outputs, and we fine-tune on those. But entirely automatically, DSPy will optimize this for you, and you can beat GPT 3.5 performance with a T5 model. So this is possible thanks to new optimizers, which tune the prompts and language model weights in arbitrary programs. They first bootstrap demonstrations, they update the program with those demonstrations, and this is done through either automatic few-shot prompting, such as with DSPy.bootstrap few-shot with random search, or finding revised instructions to plug into the program, which is what DSPy.copro and DSPy.MIPRO V2 will do. And so I've highlighted MIPRO V2 because I'm going to talk at length about how that one works. And you can also do multi-stage fine-tuning, which is what we did in the T5 example, with DSPy.bootstrap fine-tune, and that will actually update the weights of your model. And you can also compose these optimizers into complex meta pipelines. So you can imagine, and there's actually a paper that came out recently also from the DSPy team that is looking at fine-tuning and then prompt optimization and then fine-tuning again, or you start with prompt optimization and then you fine-tune. So all of these things can be composed together to get the most impressive gains possible. And so this works incredibly well in practice. Dozens of tasks in production and in research have shown that this excels in quality or cost. So I'm going to give two examples here. In May of 2024, the University of Toronto researchers have built and optimized some DSPy programs that won the MediQA competition by nearly a 20-point margin. So here's the leaderboard for that task. The idea here is looking at medical documents and finding mistakes in the documents. So they built a DSPy program and optimized, I believe, GPT 3.5 and GPT 4 with it. And all other systems that were designed by really good researchers working on this task were beat by almost 20%. And then University of Maryland researchers in June of 2024 ran a direct case study. So they had an expert prompt engineer work on a prompt for, I believe it was like mental health tasks about identifying mental health issues on Reddit. And so they had a human prompt engineer work on prompts for doing this identification of mental health challenges. And they then used DSPy to automatically optimize the prompts. And they showed that even though the human spent 20 hours of work optimizing their prompt, DSPy was able to automatically beat them in a fraction of the time. So now I'm going to dig deeper into how the latest DSPy prompt optimizer works, MIPRO V2, which I've been teasing for a little while now. This is my research and Krista's research, and it stands for Multi-Instruction Proposer Optimizer V2. And we've done this with several collaborators, both at Stanford, KTH, UC Berkeley, and Basis. So I'm going to define the problem setting of a prompt optimizer for us all. And I've sort of been talking about this the whole time, but it would be nice to formalize it. So in our prompt optimization setting, we have three things. We have our inputs, which are basically training and validation data. So in the case where I gave that RAG pipeline, that's several questions that you might want answers to. You have your language model program, which you as the programmer have written yourself. And so here's the callback to earlier. You saw the DSPy program. Here I've made it this cute cartoony figure, but you can imagine that's your DSPy program. And you have a metric. And so in the RAG case, we typically use exact match accuracy, but this could be any metric. This could be F1 score for a classification task. This could be LLM as a judge if you have something that's more subjective or hard to measure mathematically. It could be a loss function. So anything that you can optimize, and it gives a numeric output. And so what we want to do is take these prompts, these calls to Llama, and find optimal prompts for them. And so as I gave an example earlier, this is what an optimized prompt might look like, and this is what we're trying to find. So we want to find optimized instructions and optimized few-shot examples or demonstrations that will go into this prompt. And one thing that we assume in DSPy and is active research, if you don't want to make this assumption, there's more things that you can do. But because a lot of the cutting edge models are closed behind APIs and we want to make this a tool that works for everything, we actually assume no access to log probabilities or intermediate labels for your program. So we're in this kind of difficult setting where you have to treat the language models as a black box. So some of the key challenges that come with this optimization problem. First of all, prompt proposal, because here we are rewriting the instructions, not just finding few-shot demonstrations. So searching over all possible strings is intractable, especially when we have multiple calls to language models. So we had the one that writes a search query, one that generates an answer. But DSPy programs can there's no limit to how long they can be. I've written DSPy programs with 10 different language model calls that need to be optimized. I've seen people write 13 calls that need to be optimized. There's no reason you couldn't do 100. So searching over all possible plain text strings is completely intractable. We can't do that. So we need to propose a set of high quality options that we can search over instead. And then we need to do a credit assignment problem because we don't know that swapping the prompt at the first stage of the pipeline necessarily led to all of our gains if we are swapping like all 10 prompts at a time. How do we determine which prompt actually led to different gains in our optimization? And we can't either just swap one at a time and keep all the rest constant because that's going to be an intractably expensive optimization as well. So we have to be able to swap multiple and still figure out which ones are important. So MIPRO V2 works in 3 steps. First, prompt proposal. It bootstraps task demonstrations. It proposes instruction candidates with a language model program itself. And then it does credit assignment by doing a joint optimization with Bayesian learning. And I'm going to go in detail about what each of these steps entails. So first of all, bootstrapping our task demonstrations. So given our language model program, our inputs, and our metric, we need to find examples of our task working to use as few-shot examples to plug into the prompt. The way we do that is by simply running your program. So we can see I take a training input, I run it through your program, and so I've generated one search query. I can append it to the context, and I generate a second search query. And then using that context, I generate an answer. So I've gotten 3 outputs here in our program, the 2 search queries and the 1 answer. And I run it through our metric that will check exact match accuracy on our answer. And it maybe returns that this was bad. So given that we know that this didn't work, we'll discard these outputs and we'll try again. So we'll take another training input or even the same one and try again with just resampling from the language model. And we'll run it, we'll get a search query, we'll get a second search query, and we'll produce an answer. And maybe this time it worked. So we can say that this is an example few-shot candidate. We make an assumption here that all of these intermediate outputs are at least partially correct because it was able to get us to the correct final answer. And in practice, because we try a lot of things and search over combinations, it doesn't matter if maybe one of these search queries was bad because once we do the few-shot optimization, we'll discard some of the cases that don't work. But yes, we make the assumption that all of the outputs in your intermediate steps of the program are correct that got you to a correct answer in the end. And so now we have a few-shot demonstration. And that's exactly what we plug in here, is this, this full demonstration that shows context, question, rationale, and answer. And we'll plug several of those into your prompts and find which ones work the best. So that's what we're trying to build here. And I think one thing I'd like to highlight is the rationale part. Because I think when people think of few-shot demonstrations, they don't often think about bootstrapping the rationale as well. But in my mind, that's actually a key contribution of DSPy and a key thing that sets it apart and makes it better than other few-shot demonstrations. So typically, if you have a data set, you could produce all of the rest of these parts. You could say, I know what the gold documents are, I know what my question is, and I know what my answer is, so I'll plug in a bunch of few-shot examples. But in that case, you don't have a rationale that works to serve as a way of telling your language model how to think about the problem. And so I think it's pretty cool that DSPy will find good examples of how to think about the problem and put those in your prompt as well, basically teaching your language model how to do the chain of thought itself. The next thing we do is propose instruction candidates. So the key idea here is grounding, which is understanding your task. So we do a couple of things to understand your task and write better instructions. Remember, we're finding both few-shot demonstrations and the plain text instructions that parameterize this prompt. So we have program-aware optimizers, which essentially will take your DSPy code and read it and have a language model summarize it. So we feed your code directly to a language model, and I think because the DSPy syntax is so similar to PyTorch, it understands it quite well. And so I guess it's intuitive, hopefully. And so it produces this summary of your program. So in this example, this RAG example, it will say that this program is designed particularly in answering questions from a given context. It uses language models to generate search queries. So it generates this summary of your program that it can use to understand it and potentially write better prompts. We also make the optimizer data aware. So we'll take examples of your training data, the inputs and outputs, whatever you provide to DSPy, we'll show that to a language model, several rows from your training examples, and ask it to write a summary. So here's what it writes for Hotpot QA. It says the dataset contains trivia-style questions from a wide range of topics like music, film, history, and literature. Questions are well structured, so it goes into detail about what it observes about your data. And I think this is actually an active, interesting area that you could potentially add in even more complex analysis. So we really just feed it directly to a language model right now, but I think you could build a more sophisticated pipeline as well that says, maybe makes hypotheses about your data and tries to write rules like, this is what should work, this is what shouldn't work. And we can talk more later about that as a next step. But right now we are looking at it and just summarizing broadly what your data looks like. We also make it demonstration aware. So recall that we just bootstrapped those demonstrations, and we can plug those into the context of the language model as well, and say, now, given that we have this path that worked, we generated these search queries and it produced this answer, what worked, what didn't work, and keep that in mind when you're writing a prompt as well. And finally, we give it prompting tips. So the things that everyone's familiar with, the secret sauce that you try with your language models. Things like don't be afraid to be creative, include a high-stakes scenario, provide a persona, all of these things that as a human prompt engineer you might try and just see what works. So we take all of this and we feed it to a language model. We have our program summary, our data summary, your bootstrap demonstrations, prompting tips, and we say rewrite these prompts. We give it the prompts, the templated prompts that I showed earlier, and say rewrite these into better prompts. And so here are some examples that the MIPRO V2 proposal generator comes up with. So use a language model to generate a detailed and accurate answer to a given question by providing the field's context and producing the field answer. Consider specific details of the question, extract the most relevant information. So it's just different ways of saying it that are contextualized by the task itself and what you're trying to accomplish. And the final step, now that we have proposed instructions and few-shot demonstrations, we want to optimize the combination of both of these. And the key idea here is that MIPRO uses a Bayesian surrogate model to do this credit assignment. So I'm not going to get into too much of the nitty-gritty details of the Bayesian math here, but the high-level thing is that we use something called the structured tree parson estimator, which has a belief over all of the different candidate variables that you're optimizing over. And so it has a belief that a given variable is positive towards getting a good score, or a belief that it is negatively contributing towards getting a good score on your metric function. And so what we'll do is we'll actually just randomly sample, we'll use a library called Optuna behind the scenes, which is a hyperparameter optimization library. And you can really think of this as a hyperparameter search. What is the right setting of all of these variables? So we have a demo set of all of these different demonstrations that we bootstrapped and all of these instructions that we found using our proposals. And we'll say, let's try instruction 1, demo set 3, or something like that. And we will say, okay, that worked well, and so we're going to up our belief that these are good. And then we'll say, I'll try demo set 3 and instruction 2, and those got us a low score on our metric when I ran it on my validation set. So now I'm going to lower my belief that those are good. And as I said, behind the scenes, there's actually 2 beliefs. I've just shown it as one bar here, but you have a belief that it's good and a belief that it's bad. And that's just the way that the structured TPE algorithm works. But yeah, you keep sampling these and keep updating your beliefs. And every few mini batches, we will take the ones that are performing the best and run it on the full training set and say, how high of a score does that get? Because what we're doing here is running this on mini batches. So if you have like 200 training examples, we'll try it on just 25 just to get a certain belief that it's good quickly, efficiently, and for low cost. But when we find a candidate that's especially promising, we'll try it on more data to get higher confidence. And ultimately, we'll select the combination which scores the highest on your validation set. And that's essentially how we're finding all of the different few-shot demonstrations and instructions that parameterize your program. So how well does an optimizer like MIPRO V2 work, actually? We have a benchmark called LangProbe, which is essentially meant to measure this. So this is something that's an ongoing work as well. This is what we have in the current paper, are these 6 tasks. But if anyone here is using DSPy, or if you will use DSPy after the talk, I'd love for you to talk to me about what you're building with DSPy, because this is something we're actively extending to more tasks. And what we really want to capture is how people use DSPy either in production or in research in actual applications, because we are building further benchmarks to test our new optimizers and also to show people what language models work the best with DSPy. For example, do I pick Llama? Do I pick GPT-4? Do I pick Mixtral? All of these questions are going to be answered by benchmarks like this. But essentially, this is what our benchmark looks like. Right now, we have several different tasks, so Hotpot QA, Iris, heart disease, Scone, Hover. And we have different programs that we've written to solve these tasks in DSPy. And they have different numbers of modules to optimize and different numbers of language model calls. And they all have different metrics. And we want to expand this to like 30 tasks. But let's look at what these tasks actually look like in case you aren't familiar with any specific ones. I'll just show 3 quick examples. So Hotpot QA, this is the one I've been going through this talk talking about. So we have a question, for example, when was the Houston Rockets point guard recruited by Frank Sullivan born? And this is a tricky question because it doesn't say when was this person born. It kind of does a wraparound way of asking when it's like they were recruited by this they were recruited by Frank Sullivan, and when were they born? So first you can do a search and find who did Frank Sullivan recruit, and you find out that he recruited Jeremy Lin. And now you can search Jeremy Lin, and you find that he was born August 23rd, 1988. So you need 2 different Wikipedia articles to answer this question. And so we'll say August 23rd, 1988. And so that's one of the tasks we try to optimize, and we use this multi-hop retrieval program. Another task that we try to optimize is the hover task, which is claim verification. So this is a particularly tricky claim to verify. The MVP of a game, Red Flaherty, umpired, was elected to the Baseball Hall of Fame. So you have to look over the different MVPs of the games that Red Flaherty umpired and figure out if those players were elected to the Baseball Hall of Fame. And so if you search enough Wikipedia documents, you'll find that he umpired the World Series in 1965. The MVP of that game was Sandy Koufax, and Koufax was later elected to the Baseball Hall of Fame. So this is like a really complicated problem for a language model to solve that involves a lot of different searches, and ultimately it should verify that the claim is true. And the final task that I'll demonstrate that we optimize for is this Iris task, which many of you will be familiar from some intro ML classes. A lot of times we'll use this data set. I think it comes bundled in SciPy. But essentially what we're looking at is, given these variables, the sepal length, sepal width, petal length, and petal width, what species of iris are we identifying? And so the way that we actually solve this with a language model is a single call. Instead of making a multi-stage program, all you do is give it all of these variables. So you can imagine giving it a row from the table, just saying sepal length 5.1, sepal width 3.5, and just say what species of iris is this. And we want to optimize that prompt as well and see what we can do with that. So here are our results. These are our different optimizers that we test, and this table, I'll just keep extending it. But this setting here is the zero-shot setting. So this is where we do not put any few-shot demonstrations in the program. We just optimize your prompt. And the finding here is that zero-shot MIPRO, so ignoring that bootstrap demonstration step, is performing better than not optimizing your prompts at all. So essentially, optimizing instructions can deliver gains over the baseline templated signatures, and in particular, this grounding process of looking at your program, looking at your data. It seems to help it make observations and actually optimize your prompts there. The next setting we explore is demonstrations only. So this is just bootstrapping the few-shot examples. Here we are not rewriting your prompts at all. The plain text instructions stay in that templated format that DSPy automatically comes up with. And instead we just look at running your task several times, collecting those outputs and plugging those into the prompt. And we optimize in two ways. We do a random search. That's what that bootstrap RS means. And we do a Bayesian bootstrap, which is essentially using that structured tree parse and estimator that we use for MIPRO. And what we find here is that the Bayesian is outperforming random search on the 3 tasks that we ran that one on. And also that the gains from bootstrapping your demonstrations far and away bypass what you're getting from just optimizing the instructions. It's so much better to, if you have to choose one, just optimize your few-shot demonstrations. It's so significantly better. You can see those gains are much larger from optimizing just your few-shot demonstrations. And an interesting thing about this is that the demonstrations that you actually plug into the program are very important. So I think the idea behind showing this plot here is to show the variance. What we're really doing here is we have a bunch of different few-shot demonstrations that we can plug into your program. We've bootstrapped, say, like 50 different ones, and we can try all the combinations of these. And so what you see with these blue dots is the validation score of running with that set of few-shot demonstrations. And we're just randomly sampling each time here. And you see this massive variance in how high quality it is, and it's just a few really good cases that stand out and actually do really well in your program. So this is something that understanding more about is useful for future research, and I've already seen some papers starting to come out looking at like how do you select the optimal few-shot demonstrations. But it's really interesting to me that there isn't really a clear pattern, and some few-shot examples that you could put into the context of the language model will make it perform awfully, and some will make it perform incredibly well. So actually, it's very important that you do this search. And the final case here is MIPRO, which is the optimizer that we released to the community. And you can see that MIPRO is optimizing both the few-shot demonstrations and the instructions, and across all but one of our tasks, it beats all of the baselines, and in some cases by a large margin. For example, the iris task that I showed is where we see some of the largest gains, but Scone and Hotpot also do very well. This heart disease task is interesting, and I can talk more about why I think it didn't do quite as well, but you can even see that it was only 5 points below the random search baseline. So the optimization with MIPRO was still quite good in that case. So essentially, running MIPRO V2 is often the most effective thing you can do for your language model program. And the impact of optimizing instructions rather than demonstrations is more visible in tasks that have many isolated conditional rules. So that's these last few tasks. What we mean by that is, for example, the iris task. There's a trivial solution that you can come up with. I forget exactly which variable you should look at, but I think it's something like if you look at the petal length and it's above 5 centimeters, you know that it's definitely this type of iris. So if you could figure out what these rules are, you could write them all into the prompt and then just have the language model follow those rules. And so something that I think would be an interesting solution going forward, and I mentioned this when we were talking about the data-aware optimization, is actually having your language model propose hypotheses. Like, I wonder if a petal length of greater than 5 centimeters means it has to be this type of flower. Let me write a program that actually tests this. And if the rule is true, it could add that to your prompt. So things like that, that's what we mean by these conditional rules. Hotpot QA conditional, we add interesting conditions such as like you have to capitalize your answer or you have to put punctuation. And these are things that you could put into your prompt, but they're not super obvious from just few shot demonstrations about like which things should be capitalized. Because we'll say if it's a person, it should be capitalized. If it's a place, don't put punctuation. Stuff like that that can really be described by your instruction alone. And then for the heart disease task, it's also similarly a classification task where you're trying to predict based on people's cholesterol, age, gender, all of these properties, whether or not they have heart disease. So on these conditional tasks, the instruction optimization is often more significant than it is on more simple tasks or more well-known tasks like RAG and NLI, things like that. So there are a couple key lessons about what I've discussed here today, and then I'm happy to open the floor up to questions as well. But some of our key lessons here. So natural language programming. Programs can often be more accurate, controllable, transparent, and even more efficient than just single large language models. So instead of just having something like ChatGPT that answers directly based on you give it a question and it produces an answer, instead it might be useful to hook it up to a retrieval engine or to make a call to another API or maybe some sort of entity extraction. And you can write a whole program to do that instead of just making it a single end-to-end language model. The second takeaway is that you need declarative programs, not implementation details. So high-level optimizers can bootstrap your prompts or weights or whatever the next paradigm deals with. And what we're trying to say here is instead of thinking about what data do I need to collect to fine-tune Llama, or what hyperparameters and what learning rate do I need to figure out and set, and all of these high-level details that you could be, or all of these low-level details rather, that you could be trying to figure out how to optimize. Instead, you should take your time as the human expert to think about how the problem itself should be approached and how the problem should be solved, and leave the optimization to the framework. Because we can optimize your prompts, we can optimize your weights, we're working on RL optimization, and whatever the next thing that comes along, we can add that to DSPy too. So really, the value of the human is as the developer, as the architect thinking about how to solve the problem, not necessarily as the person writing the code to fine-tune the language model. So like the rest of computer science, machine learning is finally becoming truly modular. You can write algorithms that directly learn to process your domain's high-level objects, such as questions, and not these machine learning paradigm-specific parameters. So finally, I'll talk a little bit about the impact of DSPy. So this blog post from Hayes Labs was showing that for red teaming language models, you can write a program in DSPy, and you can find prompts that will break your language models 44% of the time on this safety benchmark. Whereas if you just run the prompt's default, it would respond 10% of the time. So you get a 34% direct gain, or if you look at it as a proportion, it's a 70% increase in success rate in red teaming language models when you optimize them with DSPy. So this is a company that is essentially doing this sort of jailbreaking process, and you can automatically do it with DSPy. We have some articles written. Prompt engineering is a task best left to AI models. And demand is skyrocketing for prompt engineers, one of the hottest roles in AI, and some say it won't last. So essentially, we can automate your prompt engineering, and I think that is a powerful thing that you should consider doing. So I'll stop on this slide for a moment if you guys want to scan any of these, but here are the 3 things that I would recommend doing if you want to learn more about DSPy optimizers. First, we have a tutorial for getting started with DSPy. And so that's just how do you actually write your program, how do you format your data, how do you write your metric to run everything with DSPy and optimize with DSPy. If you are curious about MIPRO V2, our state-of-the-art best prompt and demonstration optimizer currently in DSPy, we have a thread, a Twitter thread, and a notebook on how to get started with MIPRO V2. And if you are really interested in the technical details beyond what I've gone over in this talk, we have a paper on archive as well that really goes into all of the tasks and all of the things we tried and all of the lessons that we learned, and all written up in about 30 pages for you to read there. So those are the 3 calls to action I have. So I guess the final question, is this the path to AGI? Well, Omar Khattab, our leader for DSPy, certainly thinks it's the path to API, artificial programmable intelligence. So, and I've left this slide in as sort of a joke for a lot of the talks, but actually, if you've been following the AI news today, OpenAI released O1, which is their new flagship model. And in my opinion, the key takeaway from how O1 actually works is that they are, and they don't announce everything, but I think one of the key insights is the test time compute that they do, where they produce a ton of different outputs, find the ones that work well, and then I believe that that's what they use as their RL signal. So they have some sort of metric of whether this answer was correct or not. They try a bunch of times, probably with GPT-4o, which is already one of the best models in the world, or the best model in the world, and they find reasoning traces that work well, and they use RL to encourage the model to follow those traces better. So a lot of these ideas that I've been talking about in DSPy of bootstrapping your reasoning and then fine-tuning on that or optimizing your prompts on that, I think that's what OpenAI is working on to build the best models in the world. So, I mean, I put this as a joke, is this the path to AGI? But I mean, maybe that's what we're talking about. So, yeah, that's all I have prepared. So I'm opening the floor to questions now, and thank you all for your time.
If you want to ask a question, please raise your hand. I'll bring the mic to you so we can record it.
I have 2 questions. First question I have is there a way to enforce certain structure for optimized prompt? You mentioned prompt tips, but for example, if I want to have specific XML tags in specific order, if that's possible. And the second question I have is whether you can use LLM as a judge for metrics, right? If it provides numeric value as an output, can you use LLM?
Yeah, great questions. So the 2 questions are the structured outputs and using an LLM as a judge. So for the structured outputs, you can enforce this in DSPy. There's actually 2 things. We have typed predictors in DSPy, which can at least enforce the type of output and ensure that if you want a number, you can get a number. If you want a string, you can get a string. But for something like XML, there's other ways you can enforce that in DSPy. So DSPy has something called assertions, where you essentially write a bit of code that looks at an output, and it could be an LLM-based assertion, but for something like XML, you could put in an XML parser and say, given this output, run it through the XML parser. If it compiles, that's good. If it doesn't, then that's bad. And what the assertion will actually do is, this isn't necessarily the way that it changes the prompts, but it's actually the way that it changes the control flow of your DSPy program. So if the assertion fails, then it will explain in whatever way, like you basically put a plain text string of what it means for your assertion to have failed. So you could say like the XML didn't compile or something like that as what happens if this assertion fails. And it'll plug that back into the prompt and it'll say assertion failed on this output, try again. And so we have 2 things in DSPy actually, assertions and suggestions. And a suggestion is just basically a lighter assertion where it'll try a certain number of times and if it fails, it'll just continue. But if your assertion fails a certain number of times, it'll crash the program. And so you can enforce structure through things like that. And then DSPy also works with libraries such as SGLang, which can also enforce structured output generation. So if you use a library like that, alongside DSPy, you can make even stronger guarantees about that. And I believe your second question was about LLMs as a judge, and that is something that we've also done. So I didn't show it in this talk, but we have other tasks where we've written LLM as a judge programs. And some of the work that I'm doing this summer, I use LLM as a judge and optimize that as a metric. So not only is that something you can do, but interestingly, if you write it as a DSPy program, your LLM judge, you can optimize your LLM judge to correlate with human feedback, for example. So that's something that we do as well, and that works. So LLM as a judge is a perfectly good metric to use. Awesome.
Question at the very end.
Thank you for the wonderful talk. I had a quick question. So like the thing that is being optimized is like, hey, the task, like Hotpot QA or whatever, and the LLM as well. So you presumably would have different prompts that would be generated for different LLMs. How varied have you seen them to be? Like, let's say from Llama to 7B to 3.5, GPT 3.5 to GPT 4.0.
Yeah, that's a great question. So there's actually a lot of variables at play here because you can change the language model that's writing your prompts. You can also change the language model that's running your task. And the prompt that works the best for each language model that's running the task might be different. The prompts that it writes based on the prompting model also may be different. And so one thing is I notice that one thing that I think is an indicator to me that the instruction optimization is fading away from importance, but the few-shot demonstration optimization is here to stay, is that the larger the model gets, the less it seems like the exact phrasing of the prompt seems to matter, the more the few-shot demonstrations matter. And when we were optimizing some small models, really, really weird prompts would work, where like we're doing hot pot QA and you plug in, as the plain text instruction, say like, what is the score of this basketball player in this game or whatever, in the like 1965 championship, what did this player score? And that prompt actually works better across your whole data set because these small models, like they have weird quirks and weird behaviors. But what I would say is like I have noticed like a decent amount of variation, but one thing we tested is if you optimize prompts on one model and run it on another model, does that work? That does work, so you can theoretically optimize your prompts on a smaller model, maybe not a tiny model because you'll end up with super weird prompts, but you can optimize them on a smaller model and then use them on a more expensive model. And the other thing I've noticed is that GPT-4 writes decent prompts. I've actually been personally impressed, and I haven't benchmarked this, but this is what the idea of having LangProbe and expanding it would be. But Llama 3.170 billion has written some really, really nice prompts for me. I think that's actually a great model to use for prompt engineering. Does that answer the question? Awesome.
Fantastic job. Thank you. Thank you for the presentation. Quick question as a team maybe. What's your primary focus on? Is it observability or access to DSPy? What's the next V3 taking us to?
Yeah, it's a great question. So DSPy actually has a roadmap on the GitHub repository. The cool thing about DSPy is as an open source library that's expanding quite quickly, there's a lot of people working on a lot of different things in DSPy right now. So I think one push is like, how do we make DSPy something that like people can see as production ready, you know? And we're building Docker images and different ways of productionizing your DSPy programs. So that's what one push is. Another push is on this RL front, so using RL to optimize your programs. There's work, some of the stuff that I'm doing is how do we make a human in the loop in this optimization? So right now everything is automatically optimized, but what I often end up doing is I look at the few-shot demonstrations that it has come up with, and I will rewrite some of them myself and then rerun it to make sure I didn't make things worse. But I think it would be cool to have a human in the loop as it's doing the optimization to say, oh, I like what you've done with this instruction, or I should edit this. And so we're basically building a DSPy copilot that will allow you to optimize alongside the language model, kind of a prompt engineering assistant. So that's one avenue, and I think improving the documentation and doing some stuff where the last, I think, cool push that we have going on is maybe different inputs should have different prompts that work best. So how can we build like a routing function that behind the scenes will figure out which prompts to actually use for this particular task? And how do we actually optimize your program itself? I think that would be cool too. So lots of different initiatives with DSPy, and we're always looking for more contributors, so feel free to reach out and also just submit a PR.
There will be a last question from the audience, and if you want to ask more questions, hopefully you can connect with Michael offline and we'll figure out how to relate.
Thank you. Maybe it was covered, I don't know, I was a little late to this talk, but I'm curious about, is there any way or technique to get some sort of confidence levels in LLM response to certain questions?
Yeah, I think so I didn't cover that. I think that there's a lot of interesting work in that space. It's not really something that we have built into DSPy right now, but I think you could design it into your metric potentially, where I guess one way of producing confidence could be, and something that fits nicely in the DSPy framework is like generating a bunch of outputs to a given query and seeing how many of them are consistent with one another. I've actually seen some interesting work recently on looking at some interpretability methods for confidence prediction, where what you would do is write the answer where you do put the chain of thought reasoning and then have the language model produce the answer without the chain of thought reasoning, and use causal attribution to determine if it actually used the reasoning to produce the answer or not. So this isn't something that particular thing is not within the DSPy framework. I think there's interesting ways that we can use this notion of bootstrapping to produce confidence. And the most simple way is to run it a bunch of times and actually make confidence intervals or something. But no, I think that's really cool. I think that would be also an interesting thing to consider incorporating with DSPy, but that's not necessarily covered right now. Good question. Yeah.